Okay. So, hello everyone and welcome to today's session. Sorry, it's a little delayed today. That's why started at 6:30. I had some work. So sorry for that. But let's get started. So this is our last week of tutorials, I suppose. Uh, People with their mics on, if you want to speak, you can switch your mic on. Otherwise, you can mute it. Satinder Pal Singh, your mic is on. Yeah. So feel free to interrupt me when you want to speak or ask something. So before that, any questions from the previous class? Actually, before we start, there was one query regarding reliability curves, right? Reliability of using a Weibull distribution, and we had a problem with that. The question was, one second. The question was, I think it was back in week 6, I guess. Yeah. I'll share my screen. How do I share screen? So the question was, no, not this. Is this? No, not this. Week 7. No, not this as well. Maybe week 5. Week 5. Assignment 5. Can't find the question at all. Please give me one moment. I'll try and find week 6 assignment 6. No. Okay, I can't find that. The question basically was given beta and eta, that is the shape of the curve and the scale of the curve. We had to determine which of the two options, there were two options, which of them had greater reliability. So when beta is small, then your reliability is a little high. Okay, so that is the only uh, thing that you can use to actually answer that question. I can't find that. There should be, no? Let me just check. Week 6. I simply can't find that. No. Okay. Some problem. Week 5. Um, Give me 2 minutes. I'm just trying to look for the question that had something related to reliability. This was regarding the Weibull distribution. Okay. I'm just looking for that question. Not this. Week 6. Week 5 and 4. Do you know which week this question did come? Does anyone know?
Sir, week 6 assignment.
Week 6. Okay. So I'm trying to
Yes,
search
sir.
for week 6 and I'm not seeing that question at all. Maybe I'll try this. Yeah. So, yeah. Beta is given by 4 and eta is 10,000. Okay, beta is the shape and eta is the scale. Okay, for biomaterial design A, your beta is 4 and eta is 10,000, and for B it is beta equals 5 and eta equals length 11,000. So which of these are more reliable? Just focus mostly. So beta has a higher prominence. The this beta values. So whichever has a lower beta value, that is more reliable. Okay, just keep that in mind. Otherwise, you'll have to plot this curve against time and see what the distribution looks like, which is hard to do. Okay, you need Excel and things like that. But which just focus on beta values. The lower the beta value, the more reliable it is. Yeah, that is the answer for this. Now, coming to the last week questions, we'll do some practice things. So in this week you studied mainly some again designs, and then you did linear regressions, and you also did something known as control charts, just to see whether a system is within your control or not. And there are different ways to find that out. Okay, so we'll just do some practice problems there. The first one is you're given a data set and you need to do some regression analysis. So you're given a data set which has uh, drug and cell death values given like this, and you need to figure out the slope, intercept, and things like that. So what I've done is I've already tabulated this in Excel. So drug amount and cell death, and then I've plotted that. Okay, so the plot is here. Can everyone see this? Yeah, there are two lines. There should be two lines. Oh, there are two plots. Okay, can everyone see this? Maybe I'll do full screen. So given that data, this is the line I've plotted. So you can do this on Excel. How do you do that? You just go to Excel, you plot, you put these two things, you drag, maybe I'll delete this. I just select this data, I do an insert, I do a scatter plot, and then I add a trend line, and that trend line as a linear trend line. So I go to more options, linear trend line, and more options. Wait. More options, linear. I display the equation on the chart, display the R squared value. Okay, R squared tells you how well your line model that is this line linear regression that you're doing fits your data. Okay, that is R squared. So that's basically 1 minus residuals SSEs by SST, where SSE is sum of squared errors and SST is sum of square total. Okay, so 1 minus SSE by SST is nothing but R square. The higher, so R square value ranges from 0 to 1. 1 means your line is perfectly fitting your data. Okay, so this is actually a pretty good fit. 0.97 is a pretty good fit to our data. So this line is sort of predicting the data well. Okay. So let's answer some questions based on that. There were a bunch of questions based on that. What is the slope of the relation? So we have the, so please interrupt me if you have questions. We have the equation of the line, which is of the form y equals mx plus c. So m is the slope. So m here is 2.2857. So the slope is 2.2 or 2.3. Okay, 2.28, which can be also approximated as 2.3 if you round off. The slope is 2.3. The intercept is given by the c, which is minus 59.33. Okay, so at a value when x equals 0, y will have a value of 59 minus 59.33. So also, what is the r squared value? It's 0.97. Okay, there are, you should also know formulas for adjusted r square, and okay, it's given in your lectures. So please also note down what, so the formula for adjusted r square is. I don't remember it on the top of my head, but you need to know that as well. But here I have just asked for r square value, and that is nothing but 0.9796. You can also do this by calculating sums of squared errors and sums of squared total. We have done this in previous classes, previous tutorials. Please refer to that. I think in tutorial 5. So 1 minus SSE by SST gives you your R squared. How many degrees of freedom of error? So for a linear regression, your degrees of freedom of error is given by, so I'll just write that down, is given by uh, number of data points minus number of parameters. So how many parameters do we have here? Anyone? How many data points do we have first? Yeah? Anyone? Anyone can tell me how many data points do we have? You can look at the screen and tell me. How many dots do we have? Anyone?
6.
Yes. We have 6 data points. And how many parameters do we have? We have 2 parameters. One is your drug amount of drug that you've given and the response, that is cell death. So these are 2 parameters. So 6 minus 2 is 4. That's your number of degrees of error. Okay. So number of degrees of error is given by number of data points minus number of parameters, which is 4. So these are some questions that can be asked on sorry, relating to regression analysis. Okay. Also, there's a question based on data one table, what will be the drug concentration for 30% cell death? So how do you calculate that? Can someone tell me an approach to that? So to do that, you have the equation of the line, right? Y equals 2.2857x minus 59.33. So in the place of x, you replace 30%, and that will give you the y value. Uh, Alternately, you can just like do this, or 30. You can just hover over it's around. So for around 30% cell death, it is around 37. You can do this eyeballing, but to get the exact value, you can calculate, and I'll do that in Excel. So the formula of the line is 2.2857x minus 59.33, and you need to calculate at 30% cell death what is the value of how much drug do you need. Sorry, yeah, at cell death 30, 30, what is the amount of drug that you need? Okay, so you just have to transpose this. So that is basically given by 30 divided by 2.2857. Okay, this entire thing, and you need to add the intercept. I'm just transposing that. So I'm trying to find for what value of 30, for what amount of cell death, how much drug do I need? Okay, so I'm moving everything to the other side. So plus, so 59.33 plus 59.33, this entire thing plus 59.33, that's 72. 72.45. Okay. Oh, I've done something, some mistake. 30% cell death. That's 30 divided by 2.28. Oh no, sorry. I have to do 30 plus this entire thing. My mistake. This entire thing divided by 2.2857. Sorry for that. So that gives me 39.08. Okay. So so if I see this, if I eyeball here at around 39 millimolars of the drug, I get 30% cell death. So 30, if you just drop a perpendicular from 30 to the x-axis, it's around 39 point something. So that's the exact value. Okay, so drug amount needed for 30% cell death equals 39 point, how much was that? 0.08. 0.08 sorry, millimolar. Okay, you just have to use this estimated, the predicted line, use the equation of the predicted line to figure out the answer to that. Okay. The next is something to do with the control charts. So you're given this thing. So what are control charts? Anyone, can you just briefly summarize? Yeah. Can you just briefly summarize what control charts are? Okay, so control charts are basically, it's a chart of defects over time. Okay, and it allows you to know whether a system is within control or not. So if there are a lot of defects, then the system is going out of control and things like that. Defects could be anything, deviation from the normal, what you expect, and things like that. Okay. There are different types of control charts, NU, CP, things like that. Okay. Please look that up in your lectures when each of those charts can be used. For example, this here, so a factory is making switches. Every week, 8 samples are taken, and out of that, the number of defective samples are tabulated here. So you can represent this by using a C chart, because your number of samples every week are constant. It's 8, and you're just depicting the number of defects here. If it's proportion, then you use a P chart. Okay, and the charts also vary if you have different numbers of samples taken every week or whatever, every time step. So based on this data given, you need to calculate certain things. So first thing, what is the standard error of the data? That's easy. You need to calculate standard deviation and divide that by root n. Let's do that. Let's use Excel for that. So 4, 5, 6, 3, 2. I'll just write those values down. Let's use a different sheet. 4, 5, 6, 3, 2. 6, 4, 5, 3, 4. 6, 4, 5, 3, 4. So I just calculate standard deviation of sample of this entire thing divided by SQRT of, how many samples do we have? We have 10 samples. Okay, so that's 0.41. So that's my standard error. Oh, did we miss or write something wrong? 45632. 6, 4, Yeah, the data is correct. We seem to be getting some discrepancy between what is says. No, I think there's some discrepancy. It says no.
So, question is, there are 20 data points. Some of them don't show in the same viewing page. You'll
Oh,
have to
so
slide to the side.
okay. No, but they have given it as for 10 weeks, right?
Well,
So I have 10 values here.
every week, 10 samples are taken. Number of weeks are
Yeah, yeah,
10 samples are taken and the number of defects are determined as given below.
yeah, yeah. So,
So 20 weeks they are doing it. For 20 weeks they are doing
no,
it.
10 weeks, no? 10 weeks.
Every week 10 samples are taken.
8 samples. So, can
Ten-
you see my screen? 8 samples are taken, and out of 8 samples, the number of defects are determined.
Oh, sorry, I'm okay. This is I'm not able to view it that well. Okay.
Yeah. So, I don't know why there's this discrepancy. Mm, I have no clue. Because, okay, let's forget that. But this is what it is. It's sigma by root n. Wait, okay, I'll just, it's sigma by root n. That's the standard error. I'm trying to figure out why it's not, why it's much smaller. It's my, sorry, standard deviation of sample. 0.41. It's almost showing there's a lot huge discrepancy between. Just give me one moment. I'll just get back. I'll just stop sharing my screen.
So this is a very important point you need. It's very straightforward. The chart is flat. Do you understand? It's in zone. There are could be if there is some special cause variation. Take 10 samples. I take an average and then I plot the average. LCL is lower control limit. It will be K where K 135. That is to get a 99.7%, right? So be plus the limit. So, okay, true. Point of an intelligent interest. So when the process is not
Yeah, so I don't know why there's a discrepancy. As far as I think, Do you guys know why? So the question is, given this series of values, you need to calculate the standard error of the data. So that is given by sigma by root n, which for me is given the data. It is 4, 5, 6, 3, 2. Yeah, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So sigma by root n is nothing but 0.41, and the upper limit is nothing but average of this thing, average of this entire thing plus 3 into this. Okay, so that is upper limit, and the lower limit is nothing but that, but just a minus sign. Oh, no, not this. Average of. Wait. Just stop sharing my screen. I'm just doing them some calculations. I'll get back to you. I'm just here. Hmm.
Fall within the USL and LSL. Okay, whereas our control in parameter is not equal to. So it's it is our and generally the value introduce charts. We look at it average chart.
So yeah, I just made those corrections, and I think our sigma by root n is correct. I don't know why that is showing up as an error. Okay, so our sigma is sigma by root n, that is root of 10 is nothing but 0.41, and upper limit is given by average of all these numbers defects plus 3 times sigma by root n, that gives us 5.449, and the lower thing, lower control limit is average minus 3 times sigma by root n, and it's given by 2.951. I think, yeah, there's some discrepancy with regard to answers from the previous year's assignments, but that's okay.
Sample population.
So,
Sir?
but this is how you need to do it. So the formula for calculating upper limit, control charts, standard error is standard deviation by square root of sample size. and then upper UCL, upper control limit, is mean plus standard 3 times 3 into standard error, and LCL is mean minus, yeah, so that's it. And also here you try and remember what kind of charts are there. So there's N chart, U chart, P chart, NP chart. Okay, so try and remember where all of these are used. Okay, basically there's a box, square. These are based mostly on are the sample sizes fixed or variable, and are you calculating proportion. So based on that, your things will vary. Your charts, confidence, sorry, control charts will vary. Okay, and if your values of your samples are exceeding your upper and lower limit in certain ways, then you can say that it's out of control. Within there are some rules for that. You need to remember those. Yeah. So when is the system out of control? When can you say that? Okay. So try and remember all these things. So that more or less covers things that have been taught. There are other things like second order designs, higher order designs. Go through them as well. They're slightly difficult to understand from my point of view, but in practice you don't actually need a lot of those things unless yeah, you're doing some specialized stuff. So any questions based on